Okay, so oh, apparently I forgot to update my quote of the day for today, so no quote of the day uh, this morning. So the plan for today is just to finish section 3.3 measures of position, um, and also maybe just quickly demo the descriptive statistics tool on the data analysis Toolpak in Excel, and then start chapter 4 probability. So I don't want to spend too much time on finishing up section 3.3. We need to get started on chapter 4, but I just wanted to mention one last little thing on 3.3 before we move on. Note that the Unit 1 exam is this week, so the materials chapters 1 through 3. The sample exam was posted last week. It's going to be very similar to the actual exam. And I recommend that you kind of sit down, take the sample exam as though it were the actual exam. Go through it. When you finish, see how you did, see how you felt. Did you feel rushed? Did you feel like there were topics that you weren't so comfortable with? Were there problems that you got incorrect that, were all from kind of the same topic? And if so, maybe, go back and look through that material in the course, in either the lectures or the homeworks or in the book. But if you felt pretty good with the sample exam, then you should be pretty good for the actual exam. Again, note that there's no Proctor U for this first exam as we just get the text sorted out, make sure that all those details are in place. I don't want to make it live, during an actual exam when it's a fairly new system that we're still working on something with it. And then just a reminder, don't plan to wait until the last minute to take the exam. I would strongly recommend planning to take it on or before Thursday night. That way it gives you a nice buffer. If anything were to go wrong, a tech issue, anything like that, you have one full business day to work it out, as well as some hours in the weekend to use as buffer. So there are no extensions on the exam, so make sure that you plan to take it, you know, early enough that you have some extra time. I did post an exam one formula sheet on Blackboard in the supplemental materials folder, also the chapter 4 PowerPoints. And for those that are interested, I know there are a lot of folks doing, interested in kind of IT or computer science or data analysis, those kind of fields. I did post a few programming examples. I posted examples for making box plots, which is what we're going to talk about today, in a couple different languages in the supplemental materials folder on Blackboard. So that's all available. Are there any quick questions about the exam, the sample exam, any of the material from chapters 1 through 3, other than box plots, which we're going to talk about in just a minute here? Okay, let's move on then. So really quickly, the idea of box plots and the 5-number summary. The 5-number summary is simply it's simply the minimum, the first quartile, the median, aka the second quartile, the third quartile, and the max. So the min, 25th, 50th, and 75th percentiles in the max. One little note about the 5-number summary, and this applies to box plots as well. Sometimes when the min and max are reported, they're the actual min and max of the data set. So actually the smallest data value that you see in the data set anywhere and the largest. Sometimes they're the min and the max non-outlier data. And it just kind of depends on, I guess, context and uh, what they're trying to convey. So if by saying we found outliers, if we're saying that we think these data points are spurious, that they were the result of an input error or that they don't belong in the data set, that they're incorrect for some reason, Maybe if we were doing a physics experiment and we did the same experiment 20 times and we found a couple outliers, maybe we think, okay, that's not indicative of the actual physics going on. Maybe that's indicative of me just, if I am rolling a ball down a slope and hitting a stopwatch, maybe I just, fumbled with the stopwatch those couple of times or something like that. So maybe we throw out those data points and we report them in the max non-outliers. Or in another case, we might, accept the fact that maybe there are outliers, particularly if, say, we're looking at economic data, for instance, we'd expect there to be right outliers, and those are often important data points. So we might want to include those, and we want to take the actual min to the actual max in that context. Again, it's with stats, that usually from a certain point forward in the decision-making process, everything is completely objective and formulaic, but usually that kind of that seeming objectivity and set of formulas hides the fact that before that there was a decision-making process, right? We had to decide what formulas to use or what approach to take. So, but that is the 5-number summary. If we have, say, a data set with only 5 data points, say like the Ashley data here, well, I know that the min is going to be 5 and the max is going to be 11, obviously the lowest and highest data value. And if I look at the median, 8 right in the middle there, and if I look at Q1 and Q3, well, the 5 would take us from 0% to 20% on our percentile chart. 7 takes us from 20 to 40, 25% is in there. So if n equals 5, I suppose, for n equals 5, I suppose our 5-number summary is really just listing the data set. So not a super interesting 5-number summary there. But if we look at something like, say, the salary data, and I want to put this in order. So let me do that. 25, 28, 28, 28. So I've gotten those 4 data points taken care of, and then 30, 55, and 100. Well, I know that my min is 25. My max is 100. I know my median right in the middle here, 3 above and 3 below, is going to be 28. That's my median. Then I need the first and third quartiles. There are 7 data points here, so each data point gets a swath of the real line between 0 and 100% of about 14 percentage points. So 25 is going to go from 0% to about 14%, 28 from about 14% to 28%. That's going to be my Q1. And then by symmetry, not the highest, but the second highest is going to be Q3. We're going from roughly 86 to 100% for the 100, and then say roughly 72 to 86%, and 75 falls in there. So 55 for Q3 and 28 for Q1. And so that's our 5-number summary for the salary data. Again, nothing brand new here, just a kind of a common way to present several of these, I guess, numerical descriptive measures. I almost said measures of center, but they're not all measures of center. We have one measure of center, the median. Q1 and Q3 kind of gives us an idea of the IQR, and the min and the max give us an idea of the range. So what is a box plot then? Well, a box plot is simply taking the 5-number summary and plotting it on a graph. So I'm going to draw a swath of the real line. And here I know that I'm trying to plot this 5-number summary. It goes from 5 to 11. Guess I have a couple extra tick marks I didn't need, but it's the way it turned out. And so typically what I'll do is I'll draw an index like this. And then above the index, I'll just plot my 5-number summary as kind of vertical tick marks. So I'll make a vertical tick above 5 for the min, above 7 for Q1, 8 and 9 for the median in Q3, and above 11 for the max. So I now have 5 tick marks. The middle 3 I'll connect to make a box like this. And then the end ones I'll connect with these little lines. Often this is also called a box and whisker plot, with kind of the box in the middle and then these lines out to the side called whiskers. And we know that the actual data is pretty symmetric. It seems to be completely symmetric from all of our work before. And we see that here. We see that the whiskers are equal size. The median falls right in the middle of the box. So that is our box plot, just the visual representation of the 5-number summary. And we could do something similar down here for the salary data. So maybe we can start here at 25. And I don't really want to go in increments of 5 because I don't want to write 15 increments. Let's go in increments of 10, 35, 45, 55, 65, 75, 85, 95, 105. Okay, so my min is 25. My max is 100, so I guess right between 95 and 105. Q3 is 55. My Q1 and median actually turn out to be the same value of 28, and it's very close to 25, right? This is 25 to 35, so 28 is like here. And I actually have like 2 lines right on top of one another here. So in this case, my median is all the way to the left of my box. My Q3 is way far to the right. My Q1 is the same as the median. My left whisker is tiny and my right whisker is much longer. So I kind of have my median, my anchor point, and it seems like everything is getting pulled over to the right. My Q3 is way off to the right, and my right whisker, my max, is way off to the right as well. So this is my Q1 and median all the way over here at the left. This would indicate some right skewedness. I see a very long right whisker compared to the left whisker. I see that my median is heavily towards the left of its box, much closer to Q1 than Q3. This might make me suspect some right skewedness or some right outliers. I could also be in a situation where I see my box. This doesn't apply to either of these data sets, but just to give you an example, I could have a box that is fairly small and whiskers that are fairly long. Maybe I wouldn't see skewedness here, outliers on one side or the other, but with such a long whisker size relative to the box size, right? This box represents 1 IQR. It sure looks like there are some outliers here, maybe evenly distributed on both sides. So maybe we don't see evidence of skewedness, but maybe we see some evidence of outliers. One of the downsides of, where did I put it here? One of the downsides of using actual min and max is if I see something like this and I see, oh, okay, I think there are outliers here. I think there's at least one outlier to the left and at least one outlier to the right, given how long these whiskers are relative to the box. How many outliers are there? I really don't know. I'm pretty confident that there's at least one on each side, but there might be 3 on each side or 1 on the left and 3 on the right, or I'm not really sure. If I make my min and my max non-outlier min and max, then I could end up with a box plot that maybe looks like this for, say, the similar data as above, where these are my non-outlier min and max. And then what you'll sometimes see is that the individual data points that are the outliers are represented with dots. So this gives a little more granular information about the outliers. So if I see something like this, I can see very clearly that I have 2 dots on the left, so there are 2 outliers on the left, 3 dots on the right, 3 outliers on the right. But in my mind, that kind of takes away from the real meaning of the box and whisker idea is, well, what do the whiskers mean now? They're just kind of going out to the non-outlier data points. Like, so you lose a little bit of efficacy there, but you get a little more granularity when discussing the outliers themselves. So just as everything, there are trade-offs, there are decisions to be made. I don't think there's one way that is universally better and one way that's universally worse. It's a question of what you're trying to convey, what the important point is you're trying to make. If you're really interested in the outliers, having more granularity in the outliers is probably better. If you're more interested in the structure of the data set overall, maybe the black representation here is a little better. So any questions on anything in chapter 3? All right, give me a second to get my screen share swapped over here. I'm going to get Excel started back up, and we're going to take a quick look back at our chapter 3 demo. And for this one, sorry, I have 2 screens going here, and I always forget before I open a file that I have to paste it in chat before I open it, or else it won't paste right. So I just pasted the file in chat for the data analysis demo for chapter 3. Now I can open that up. There we go. And I think I had briefly showed you how to do this before, but I just want to go through it quickly again, just mainly because now that we've gone through chapter 3, we will recognize a little bit more of this, this output. There we go. Okay. Okay, so we looked at these data sets before, and I think before we had cranked out this this list of descriptive stats, we might not have. So let's go through doing that again. So to do that, we want to go to data, and we want to use our data analysis Toolpak. Now, you might not see this when you look over in data. You might not even see an analyze box at all, or it might have some stuff and not have the data analysis Toolpak. So let's go really quickly through how to install that. So just in case you don't see it there, if you go to File and then go down to Options. So File Options, and we're looking for add-ins here on the left panel. Go to add-ins. And we see down at the bottom, we have Excel add-ins. We're just going to click go next to that. I think that's the only, oh no, there's other add-ins, but we want Excel add-ins. We see it pops up this little box here. We want to make sure that the analysis Toolpak is checked and hit OK. Solver can also be pretty useful. The other two I don't find much use for. And then if you go to your data tab, you should see data analysis now. So let's click the data analysis Toolpak. Often the first time that I open it after I've had Excel closed, it takes a little bit of time. So, but it's usually pretty quick after that, I found.
Professor, can you demonstrate opening that again?
Yeah, sure. So if you go to File and Options, you should come up with this, this pane. And then on the left here, we see general formulas data. If we go all the way to the bottom, second from the bottom, there's add-ins. We'll click that. And then down here near the bottom, can't really select anything down here, doesn't, but down here near the bottom, it says manage Excel add-ins. Make sure that Excel add-ins is chosen from the drop down and hit go. And Excel is just not wanting to cooperate. Insert joke about Microsoft not being stable. But anyway, when you get the add-ins pop up here, then you should be able to check data analysis, Toolpak, and hit OK, and then it should add it in. For whatever reason, it doesn't want to come up for me. All right, there we go. Yeah, analysis Toolpak, and hit OK. So just make sure that is checked, hit OK, and then you should see it here. And then if we go to the data tab, so up here, there's like file, home, insert, data, and click on data analysis. Then it should come up. Again, it takes a little while to come up the first time. There are some things we'll use later, particularly regression, we're going to use quite a bit later in the course. But here we're going to use descriptive statistics. Hit OK. And our input range, we can use our last digits of weights. So I'll click the first cell. I'll include the label too, just so we know what data set it is. And then I'll hold shift and click the last cell. We see it's grouped by columns. That's good. I'll check labels in first row so that so Excel knows that that cell with last digits of weights is the label for it. We'll output it in a new worksheet ply. You could output it in the same worksheet if you wanted, but we'll output it in a new worksheet ply. Keep things separated. And I guess we'll just do like summary statistics. You can also do like, if you want, the third largest, value in the data set or something, you can do that. Kth largest or kth smallest, but we'll just do summary statistics. And this is our output. So if I zoom in a little bit here, we can't really read these over here too well. So if I look at this divider between A and B, where my down arrow switches to like a kind of left-right arrow with your cross kind of deal, if I just double click on that, that'll resize so that I can read everything. And I see, for instance, the mean for these last digits of weights data. This isn't really a sensible thing to do. I really wouldn't want to compute a mean or something for this because it's more categorical data, right? It's not the full weight, which might be ratio data, but it's just the last digit of the weight, just plucking that last number off. So this probably isn't very meaningful for this data set, but just to show you what you can do for a data set. The mean would be 2.48, standard deviation and sample variance given here. We see a number that's skewedness. This is not the Pearson coefficient of skewedness. This is a different metric for skewedness. Kurtosis is a little bit like skewedness, but it's like how peaked or how pointy the distribution is, how close it is to its measure of center, kind of. We see the range, the max and the min reported, also the sum of all of the data points and the count. So, what are the most useful ones here? Well, probably these two because they're kind of a pain to compute. The mean because it's so often used, and maybe the count would be another one that, just knowing what your sample size is. Some other ones like range, max, and min might be useful in other contexts. Oh, we also see the median, which I think I forgot to point out. So that's something that we can use Excel for. You're free to use Excel on the exam. So you can even use the data analysis Toolpak and get your sample statistics really quickly off of this. So kind of from slowest to fastest is doing it by hand with using a calculator just to do the arithmetic. A little bit faster to maybe type it in the calculator and use the calculator tools. I don't recommend that because we haven't really talked about that at all. Probably a little bit faster than that is just popping the data over into Excel and using like equal average or equals median, kind of coding that in yourself. And even faster than that is to use this data analysis Toolpak with descriptive stats. On the plus side, you get an answer very quickly. On the minus side, well, what if you want population variance, right? Or what if you needed the mid-range or something like that? So you might still have to do a little bit of work, but you can get a lot of information really quickly using that built-in tool. So any questions in chapter 3? That wraps up all of chapter 3 that I wanted to discuss. Okay, then. So the plan for the rest of today and for the next few classes is to start chapter 4 on probability. So again, I popped this PowerPoint in the chat a little earlier, and also it's on the Blackboard site. And I guess our quote of the day today can be this fun little quote from Mark Twain as we wrap up chapter 3, where we talked about, tons of different ways to report, say, a measure of center, or several different ways to report a measure of variation. Mark Twain says, facts are stubborn things, but statistics are more pliable. So, the story that you want the statistics to tell is maybe some would say as influenced by the decisions made by the person computing the statistics. Even if you're computing, doing the right computations and all of that, you're making decisions on what to report, what not to report, and so on. The narrative that's told can be as influenced by those choices as by the actual facts and the actual data. There's another saying in stats. I've tried to find the source of this, but I can't find it. But it was from a statistician, and the quote goes something like, you let me choose the denominator and I'll make the stats say anything you want. In other words, the denominator being like the sample size. You let me choose the population, you let me choose the group to study, and I can select a group so that the stats come out whatever way you want. Quite a true statement. So, okay, moving into chapter 4, probability. Here we're really taking a real shift, a real kind of 180 change in the way that we look at things. And in chapter 1, we just kind of introduced a bunch of ideas, but in chapters 2 and 3, we basically looked at the perspective where we have a data set, we have real world evidence, let's say, or real world data, but it's not in a super nice form for us to be able to use or interpret or turn into information or knowledge. So then we look at how do we take that information from the, maybe I shouldn't be careful, I should be more careful with my wording. How do I take that data from the real world and manipulate it so it's easier for us to interpret and understand? One way that I might do that is, say, make a graph, histogram, a bar chart, a pie chart, something like that. Another way I might do that is, say, report a mean and a variance or some other measure of center, measure of variation, giving you some idea of certain characteristics of that data set, of course, at the loss of the granularity that the original data holds. So I was looking at something that came directly from the real world, raw data from the real world, how to make it more digestible. In chapter 4, we're really chapters 4 through 6, we're taking a completely opposite point of view. We're almost kind of assuming that we are like omniscient beings. We're assuming that we know everything about the system. We're assuming we know everything about how the fundamental mechanisms work. And we're saying kind of on one go of this, right? If I know everything about the population, if I take one sample of size 100 from a population of 1 million, what might that sample look like? So instead of us saying in chapters 2 and 3, I have one sample, that's the data that I have. What might the population look like? Now I'm saying I kind of suppose that I know about the population, and I'm asking what might a sample from this population look like. So we've talked a little bit before about the notion of probability. Then it's something like the chance of an event occurring. That's actually kind of a difficult thing to explain exactly what we mean, right? If I say that there's a 30% chance it's going to rain tomorrow, what do we mean by that, right? I mean, in some sense, it represents degree of belief. If you had a picnic planned for tomorrow and there's a 10% chance of rain, you probably still do your picnic. If there's a 90% chance of rain, you probably cancel your picnic and make other plans. So do you believe that it's going to rain or not tomorrow? Well, 10% versus 90% is probably going to be, you know, you either keep the picnic planned or you cancel it. Um, so that's one way to think about it. Another way to think about it is something like, well, if they say there's a 30% chance of rain tomorrow, what I think that means is that, if I were to look at, say 100 such days, 100 days where they predict a 30% chance of rain, I think on 30 of those days it will have rained, and on 70 of them it will not have rained. So this idea of probability or the chance of an event occurring or what it kind of really means in the real world is actually pretty hotly debated, or maybe even what it should mean in the real world is hotly debated, as well as what it does actually mean when you say to somebody, there's a 30% chance of rain. How do they actually interpret that? So how should a person interpret it? How do they interpret it? Hotly debated. There are, in a sense, kind of two camps. The frequentist camp and the Bayesian camp will investigate this a little bit further, a little farther down the line. But there are other camps as well that are less popular. But what is probability actually? Well, what probability actually is it's a mathematical structure. It's a mathematical model. So we have all of these difficult questions to answer when we try to say, if I'm using this model to understand something or predict something in real life, in the real world, how should I think about that? That's a difficult question. But what, at least as far as I know, that nobody really realistically argues about is, well, if I look at probability and I say this is a mathematical model, I start with some certain assumptions. I can build on that using theorems and using logic and come to conclusions from those assumptions and so on. Well, that's a mathematical model. This mathematical model is divorced from anything in the real world. It's not, the way that 1 + 1 = 2 is maybe helpful if I'm counting, I have one apple and another apple, I have two apples. But 1 + 1 = 2 doesn't only apply to apples, right? Sometimes it's convenient to apply it to apples, but it's something that exists outside of reality. It's its own thing, and sometimes it's useful in certain scenarios. Same kind of thing here. So it's really hard to make this shift, I think, conceptually. And that's why I'm spending a little bit of time on this, because chapters 2 and 3 were so real world, so data focused. And now we're switching to a completely abstract focus where we're talking about probability. This is a model. So when we say probability, it really just is probability. We define it a certain way, and that's what it is. Typically, when we're looking at examples in probability in this mathematical structure, we're typically trying to answer one of two questions, something like, what is the expected outcome of an activity? Kind of on average, what would happen? And what's the risk or the volatility of an activity? Right? If I have a population of people in, say, Pittsburgh, and I'm interested in their heights, if I were to randomly choose one person from that population, how tall do I kind of expect them to be, kind of on average? Or what's the variability in their height? Do I think it's very unusual that I get somebody that's 2 feet taller than average or 6 inches taller than average, something like that? So a probability experiment is a random process that leads to well-defined results called outcomes. So probability uses this idea of randomness. And essentially randomness is just this mathematical model that we're creating. It's just a component of it. In the real world, how do I think of randomness? So if I wanted to say, oh, like, you know, rolling a die in the real world is like a random process. It comes up 1 through 6 and it's random. Well, what I really think of there, I think the best way to think of it is really that it's chaotic. So not that it's impossible to predict. I guess if we knew enough about physics, we probably could predict how that die rolls. Although maybe quantum mechanics throws a bit of a monkey wrench into that. Um, but at least, I kind of have a gut feeling that I could predict how that die is going to roll if I had enough information from the time that it, say, left the person's hand. Um, but in reality, that's impractical to do. So by the time that the die leaves the person's hand to when it comes up 1 through 6, there's so much information that I would have to take in, so much computing power that I would need to use to figure out all of the different interactions that are going to be going on to make a prediction, that that's just impractical to do. And also, any little change in any of those conditions can change a 1 all the way to a 6. It's not like a little change in the initial, rotational velocity or something is going to change a 1 to a 1.1. A little change can change a 1 to a 6, or a 4 to a 2, or a small change in the inputs can yield a very large change in the outputs, right? Or if I had a bunch of people in Pittsburgh and I labeled them all from 1 to a million or whatever, and if I chose person 531 instead of 532, I could go from somebody who's 5 feet tall to somebody who's 6'6". So that's kind of what we mean by a random process, is a chaotic process where small changes in the inputs yield very large changes, or can yield very large changes in the outputs, and where that connection is impractical for me um, to really to model very well and very quickly. Okay, so that's the idea. Uh, that's the way that we're going to look at probability in this course. So probability is a mathematical model. When we overlay it into the real world, it gets complicated. What we mean by when I apply this mathematical model to some real world situation, what do I mean when I do that? What do I mean when I say the chance of an event is some percent in the real world? That's a fairly complicated thing to answer. Uh, that's tied to what do I mean that some process in the real world is random. But all of that question we're going to put off till a little bit later. And for right now, we're just going to look at the mathematical structure. Okay, so a couple of definitions. So an outcome is the result of a single trial of a probability experiment. We often um, model things in probability by, say, like die rolls or coin flips, something like that. So you can think of a die roll. An outcome might be like one roll of a die, and the die comes up as a 2, something like that. The sample space is the set of all possible outcomes of a probability experiment. So if I roll a die, my sample space is 1, 2, 3, 4, 5, 6 for a standard 6-sided die. And note that I'm not saying all probable outcomes or all outcomes that we expect to see or anything like that. Remember, this is a mathematical model. So when we say the die will come up 1, 2, 3, 4, 5, or 6, each with equal likelihood, that's literally what the model is. It's not that they'll be approximately equally likely, or that maybe we could roll the die and sometimes it ends up on its side or on a corner or something, and we don't know what the result is, or that it, falls down a sewer grate and we couldn't see the result. Those are all excluded. This is a model that we're making, so we get to make the assumptions. So the sample space is the set of all possible outcomes of a probability experiment. It is impossible to come up with an outcome that's not in the sample space. Now, again, when we move this over to the real world, could our model have shortcomings? Well, sure. That's a shortcoming of applying the model to the real world, but not of the model itself. If we remember from much earlier in the course, there was our kind of motivating quote for the course that all models are wrong, some models are useful. An event is a set of outcomes. It's a subset of the sample space. It could contain all of the outcomes. That's kind of a boring event because the event just always occurs. It could contain none of the outcomes. That's also a boring event because that event never occurs. Interesting events typically contain some, but not all of the outcomes. So like rolling a die and getting an odd number, that might be an interesting event to study. Rolling a die, a standard six-sided die and getting a number less than 7 is kind of a boring event to study that just always occurs. It happens 100% of the time. Okay, so some examples. We've already discussed a little bit the idea of the probability experiment rolling a die. The outcome is the number we get when we roll the die one time. The sample space is 1, 2, 3, 4, 5, 6. And some events could be something like rolling an odd number that is getting an outcome that's a 1, a 3, or a 5. Perhaps rolling a number greater than 2, so 3, 4, 5, 6. Be careful, a number greater than 2 does not include 2, so just 3, 4, 5, 6. Not rolling a 3, so rolling a 1, 2, 4, 5, or 6. These will be different events that we could talk about. Another example of a probability experiment, rolling a die 2 times. So the outcome is the numbers, say, in order that we get when we roll the die 2 times. The sample space might look like this, say 1, 1. This doesn't mean 11. This notation, by this notation, I mean 1, 1. So we got a 1 on the first roll and then a 1 on the second roll. Or 1, 2. 1, 2 would be different than 2, 1 because order matters here. The number is in order that we get. So 1 on the first roll, 2 on the second roll, or 2 on the first, 1 on the second would be 2 different outcomes in this context. And so on all the way up to 6, 4, 6, 5, and 6, 6. We can draw a little grid to represent these. So here's my first roll and second roll, let's say. And here would be 1, 1, and 2, 1, 3, 1, and so on, all the way down to 6, 6. We see there are 6 times 6 or 36 total outcomes in the sample space. I have a 6 by 6 grid of different outcomes. Some events that I could be interested in, just a few, right? There's lots of events, but for instance, rolling 2 odd numbers. So 1, 1 or 1, 3 or 1, 5 would be outcomes that are in that event. But like 2, 3 or 2, 4, those would be outcomes that are not in this event. We could look at an event of rolling a number greater than 2. So at least one of our 2 numbers is greater than 2. So an outcome like 1, 4 or 5, 6, they would be in the event, but an outcome like 1, 1 or even 1, 2 would not be in the event because 2 is not greater than 2. 2 is equal to 2. Or an event like not rolling a 3 on either roll. So like 1, 1, 1, 4, 1, 5 would be outcomes in this event, but 1, 3 or 3, 1 or 2, 3, those outcomes would not be in this event. Another example, flipping a coin 5 times. So we take a coin, has heads on one side, tails on the other side. That's kind of an aside. If we say just flipping a coin or rolling a die or something like that, without any other information given, we assume that the coin has one side that's heads, the other side tails, and that it's equally likely that it comes up either side. Same with a die, or similar with a die. A standard die is 6-sided, so if we just say we roll a die, we mean a standard 6-sided die. So it has the numbers 1, 2, 3, 4, 5, 6 on it, each of which comes up equally likely. So what is the outcome? The outcome here might be the sequence of heads and tails. So the sample space might look like 5 H's, in other words, heads on the first flip and heads on the second flip and heads on the third and the fourth and the fifth flip. That might be one potential outcome. Another potential outcome would be like, say, 4 heads, then a tails. So heads on flips 1 through 4 and tails on flip 5. Or another outcome that is a different outcome would be like the first 3 are heads, then a tails, then a heads. That's a different sequence of heads and tails. Even though there are 4 heads and 1 tail, in both cases, the sequence is different. The tail occurred on the 5th flip or the 4th flip. Those will be different outcomes. And so on all the way out to 5 tails. Now, you might say, like, could I set up a sample space as just saying, like, 5 heads, 4 heads, 3 heads, 2 heads, 1 head, 0 heads, those counting those as my outcomes? And the answer is yes, you could. We do it this way, though, typically so that our outcomes are equally likely. We'll see in a little bit, maybe not today, but we'll see throughout chapter 4 that number one, having equally likely outcomes is actually really important. And number two, we have to be very careful when we set up our sample space and we decide what the outcomes are going to be, whether it's going to be, say, the sequence of heads and tails or the number of heads on 5 flips or something like that. We have to be very careful to set up our outcomes in a way that makes it easy to make a sample space with equally likely outcomes. And sometimes this is not trivial to do. So some events could be, say, flipping all heads. Heads on flip 1 and heads on flip 2 and so on, up to heads on flip 5. Or say flipping 3 heads, then 2 tails, which would be just this one outcome, heads, 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 tails, tails. Or I have to be careful here because the wording, a slight change in the wording can make a big difference in the set of outcomes or in the event, the number of outcomes in the event, so on. Flipping 3 heads and 2 tails. Well, 3 heads, then 2 tails, there's an ordering there, right? I got to get the 3 heads and the 2 tails have to come after that. But flipping 3 heads and 2 tails on 5 flips, there's not a natural ordering there. So 3 heads, then 2 tails does count, but also 2 heads, a tail, a head, a tail also counts. There are 3 heads and 2 tails in those 5 flips as well. So there's, for flipping 3 heads, then 2 tails for that event, there's only one outcome in there. But for flipping 3 heads and 2 tails, there's a bunch of outcomes in that event. Any questions so far? Okay, so moving on to the idea of classical probability. So classical probability uses sample spaces to help determine the probability that an event will happen. And as I mentioned before, note that we're assuming essentially that we know the underlying frequency distribution before we run the experiment. So if I say I have a ferrous six-sided die, I'm assuming that like 1 comes up 1/6 of the time and 2 comes up 1/6 of the time and so on. Or if I say I have a fair coin that I'm going to flip, heads comes up 50% of the time, tails 50% of the time. Again, this is the opposite perspective from, say, chapters 2 and 3, where I said I don't know the population level information. I only know the sample level information. Here we basically like know the population level information, but we might be interested in like what happens on, say, one run of the experiment. What's the likelihood that I get this or that result on one run of the experiment? So we define the probability of an event, E, which we denote P of E, just like this. So the probability of event E is defined this way. It's the number of outcomes in E over the number of outcomes in the sample space. Extremely important assumption here. We're assuming that all the outcomes in the sample space are equally likely. So we want to be very careful to set up the way that, to set up our outcomes, the way that we set up our probability experiment, the outcomes are set up in a way that when we get the sample space, the collection of all outcomes, each of those outcomes is equally likely. So for example, the probability of rolling an odd number is 1/2. We know again that absent other information, we're rolling a die, so it's going to have 6 sides, 1, 2, 3, 4, 5, 6, and they are all equally likely. So my sample space is the set 1, 2, 3, 4, 5, 6. That's my sample space. My event E is the set 1, 3, 5. Those are the odd numbers in 1, 2, 3, 4, 5, 6. So my probability is the 3 equally likely outcomes in my event over the 6 equally likely outcomes in my sample space. 3 over 6 is 50%. So the probability of rolling an odd number, 50%. What about, say, flipping a head, then a tail, and 2 flips of a fair coin? Oh, wanted to scroll down over here, not over there. So again, I can kind of look at this and say, okay, flipping a head, then a tail, that means there's an order here. So I have a first flip and a second flip. So these are my 4 outcomes. Flipping a head, then a tail, that's the 1 outcome in my event. Are these all equally likely outcomes? Flipping a head, then a head, tail, then a head, head, then a tail, tail, then a tail. Yeah, as long as my coin is fair, as long as it's a 50-50 shot of getting a head or a tail in each flip, then these will be equally likely. So what's the sample space? There are 4 outcomes in the sample space. There's 1 outcome in the event. These are all equally likely outcomes. So my probability of the event is 1/4 or 25%. Now, what if I asked a question like, what's the probability of getting 1 head on 2 flips? Well, I could get 1 head either here or there. I would not want to set up my sample space as being like, how many heads do I get on 2 flips? 0, 1, or 2. I wouldn't want to say getting 1 head on 2 flips is 1/3 because I have 1 outcome of my event and 3 in my sample space. So this is not 1/3 like this because these are not equally likely. There are 2 different ways I can get 1 head on 2 flips. I could get the head as the first flip or the head on the second flip. So probability of 1 head on 2 flips is actually 2 out of 4 or 1/2. So I've got to be careful again with how I set up my outcomes and my sample space and so on. It might be tempting to do something like this, but to say, oh, well, there's 3 possibilities, so each one is equally likely. But we kind of intuitively know that that's not that ought not be the case if we think a little bit about it, even in the practical world, right? I mean, we're technically dealing with a mathematical model here, so it doesn't have to mesh with our practical world, but we can certainly think of examples like, if I buy a Powerball ticket, well, there's only 2 things that can happen relative to winning the Powerball. I either win the Powerball, the $1 billion, or I don't win the $1 billion. Do I really think it's 50-50? Do I really think that I have a 50-50 shot of winning the Powerball just because there's 2 things that could happen, either win the Powerball or don't win the Powerball? Uh, well, no, we wouldn't think that, right? So we actually have to be pretty careful to construct a sample space and construct outcomes that are equally likely. Okay, so next example, rolling a 2, then a 3, and 2 rolls. Again, looking up here, there's one way that this could happen. Rolling a 2, then a 3. That's our one outcome in the sample space that is in the event, 2, 3. How many total outcomes do we have in the sample space? 36. We have a 6 by 6 grid of unique outcomes, all of which are equally likely. So our probability of rolling a 2, then a 3 is 1 out of 36, or about 2.8%. So note that if we had asked something like, what's the probability of roll a sum of 5, that's not the same. Because again, there's lots of different ways that I could get a 5. I could get a 3 and a 2, or a 4 then a 1, or a 1 then a 4. These would all give me a sum of 5. So there's lots of outcomes that give me a sum of 5. And what I definitely wouldn't want to do is I definitely wouldn't want to set up my sample space as, well, what could the sum of 2 rolls come out to be? It could come out to be, I suppose, 2, like a 2 1s, all the way up to 12 if I get 2 6s. So I would not want to say, well, there's 11 of these and 5 is one of them. I wouldn't want to say that, right? But I also want to recognize that, say, rolling a sum of 5 is a different event than rolling a 2 then a 3. So again, I have to be really careful with how I think about different events, how I split up my outcomes. I could figure out what's probably rolling a sum of 5, but that would be 4 out of 36, right? Because I have 4 ways. These are the only 4 that will sum up to 5 along that diagonal there out of 36 equally likely outcomes. I could do it that way, but I would not want to set up my outcome something like that because they would not be equally likely outcomes. Now in chapter 5, we'll look at setups where we have not equally likely outcomes, and we'll develop some more math and some more ability to handle these more complicated scenarios. But at this point, we're just looking at counting number of outcomes in the event, counting number of outcomes in the sample space, and taking the ratio. So we've got to be careful to set up the outcomes in the sample space in such a way that we have equally likely outcomes. And kind of in the similar vein, if I'm looking at rolling a 2 and a 3 and 2 rolls, both of these outcomes would satisfy that event. So now I have 2 outcomes in my event. I have 36 equally likely outcomes, just like before. Probability of this event is 2 over 36, or 5.6%. So double the, wrong direction, double the 2.8% that I got before for a 2, then a 3. So I've got to be pretty careful with the details whenever I'm going through any of these problems, making sure that my outcomes are equally likely, at least as far as chapter 4 is concerned, making sure that I understand exactly what event I'm talking about, and then I'm not being too flippant or too loose with either the grammar or with the meaning of that event or something like that. Okay, so what about this example? We have a normal deck of cards here, and I have a YouTube video on just the basic idea of like how a normal deck of cards works, but the kind of crash course is that we have 4 what are called suits. We have hearts, diamonds, spades, and clubs. And we have 13 values. So this goes from ace, or 1, 2, 3, up to 10, and then jack, queen, and king. So in each deck of cards, there's, say, like an ace of spades, there's a 2 of diamonds, and so on. There are 13 times 4, 52 unique cards in a deck. No card in a deck is the same as any other card in a deck. for these ones, if we get rid of the jokers and stuff. No card in the deck is the same as any other card in the deck. So there are no duplicates and there are none missing from this. It's not like there's no ace of clubs or something like that. They're all represented exactly once. So really a deck of cards is just a way to pick out one unique item from 52 unique items. But having the different values and the different suits allows us to a little more conveniently group them in certain different ways. So my sample space has 52 outcomes, 52 unique cards, and I'm interested in what's the probability of drawing a jack or higher. And for a lot of games, even though ace is kind of like a 1, ace is quite often a high card. It's quite often the highest card, so above a king. I don't know who decided that. Um, maybe somebody whose last name started with A or something was offended that, their card was the lowest one and made it the highest one. I don't know. But for whatever reason, like you always hear of like, oh, 4 aces or something. It like, is a really good hand. So when we say jack or higher, we have to be a little bit more clear about, well, what's the context? Is ace high or low? But again, let's say that we settle that and we say, okay, ace is high. Well, what's the probability of drawing one card that's a jack or higher? Well, how many of these outcomes are in the event? Well, I have 4 values, jack, queen, king, or ace, and 4 suits. There are 16 ways to get the event. How many equally likely outcomes are there? How many unique cards that are equally likely to be drawn are in the deck? 52. So 16 out of 52, or about 31% or so. Note that 16 over 52, well, that's 4 times 4 over, well, 52 is 4 times 13. This is also just 4/13. So because each of these suits is like kind of a perfect copy of the other suits, right? There's an ace through king in hearts, and there's an ace through king in diamonds, and so on. There's a lot of symmetry to problems like this. And in fact, in probability, there often is a lot of symmetry that we can exploit. I could count the number of individual cards in here. Divided by the total number of cards, 16 out of 52. Or I could realize that symmetry and say, well, drawing a jack or better from a whole deck of 52 cards, the likelihood of getting that, it's really just the same likelihood or chance or probability. If I just looked at the hearts, if you just took the 13 hearts and shuffled them and said pick one, and I picked one, it's the same probability of getting a jack or better. Because adding in the other suits, I just add the same proportion of jack or betters to all cards. So I could either look at this as 4 of the values out of 13 of them are jack or better, jack, queen, king, ace out of the 13 values. Or I could look at it as 16 of the cards have a value that's jack or better out of 52 of the unique cards. That symmetry means that I can move back and forth between these two ideas. Now, if I asked, what's the probability of drawing a jack of hearts or something like that specifically, well, now because I'm demanding hearts, I've kind of broken that symmetry, right? So now I have to think of the deck. Now I do have to think of the deck as a whole. But sometimes there's a symmetry. Oftentimes there's a symmetry that I can exploit. And this is again another quote that I should look up the source for, but there's a mathematician who said something along the lines of like, you know, when a problem has an inherent symmetry, mathematics often rewards you if you exploit that symmetry. So looking for symmetries and ways to exploit it is useful in probability. It's also useful really across mathematics. So in your algebra course or calculus course or whatever, looking for symmetries is also quite useful. Okay. So what are some rules of probability? What are some properties of probability? Okay, the first one, by the definition of probability, probabilities always have to be between 0 and 1 inclusive. So remember, the probability of an event is the number of outcomes in the event over the number of outcomes in the sample space. But the sample space contains all outcomes. The biggest an event could possibly be is the entire sample space. The event cannot have more outcomes than are in the sample space because whatever the extra outcomes are that are in the event would have to be in the sample space. So the biggest an event can possibly be is having all of the outcomes that are in the sample space. And if the event is the same size as the sample space, if they have the same number of outcomes, then the probability of that event is just 1. So the biggest the probability can be is 1. And likewise, the smallest an event can be, well, I guess the fewest number of outcomes, if we're counting number of outcomes like 1, 2, 3, 4, 5, the fewest number of outcomes that can be in an event is 0. You can't have like -1 outcomes in an event. You can't say, here's 20 outcomes in the sample space. How many would you like to put in your event? And you can't pick -2 of them. The lowest you can get is just picking none of those outcomes. So the lowest the probability can be is 0. So it just comes right off of this definition alongside the fact that a sample space contains all of the possible outcomes. These next couple are restricted to sample spaces that have finitely many outcomes. Once we start throwing around infinities and so on, things can get somewhat strange. But we can say that if an event cannot occur, if it's impossible for it to occur, then the probability of the event is 0. The only way that an event cannot occur, that it's impossible for it to occur, is if the number of outcomes in the event is 0. If there are no outcomes in the event, it's impossible that it occurs. Every probability experiment will result in an outcome that's in the sample space, but none of those are in the event. So we'll never have a probability experiment that results in that event occurring. But if there are no outcomes in the event, the probability of the event is 0 over number of outcomes in the sample space. That's just 0. And if an event is certain, if it has to happen, that means that every outcome in the sample space has to be represented in the event. If there was even one outcome in the sample space that was not in the event, then we could run the probability experiment and get that one outcome in the sample space that's not in the event, and the event would not be certain. It could not happen. But if the event is certain, it has to include all of the outcomes that are in the sample space. The numerator has to be the same as the denominator, and that probability has to be 1. And then lastly, the sum of the probabilities of all the outcomes in the sample space must equal 1. So basically, if I took my sample space, let's say, for instance, it was my deck of cards up here, and I made one event that was like getting the 2 of hearts, and another event that was like getting the 2 of diamonds, and I made a separate event for each of the outcomes. Each event just contains one of the outcomes. And so all of my events together, kind of make up the whole sample space, and there are no duplicates. Then the sum of the probabilities of all the outcomes have to be 1. So the sum of the probabilities of all those events has to be 1. what is this really saying? This is really saying that, well, if I run the probability experiment, something has to happen. There has to be 100% chance that something happens, right? If I draw a card from a deck, there has to be 100% chance that one of these cards will be drawn. One of these outcomes will be realized. If I roll a die, 1 through 6, there has to be 100% chance that one of those outcomes will happen. Okay, so any questions so far? So now we're going to take just briefly a little bit of a glance back at chapters 2 and 3 and say, okay, how do these tie together? We have these two seemingly very different structures. How might we think about them tying together? And that's where empirical probability comes in. This uses actual data or observations, in other words, samples, to guess the underlying frequency distribution. So here we're saying we don't know the frequency distribution, but we can take a sample, we can make a sample frequency distribution, and we can say estimate the probability as, say, the frequency for the class divided by the total frequency in the distribution, the number of individuals in the sample who meet this criterion for this event divided by the total sample size. So that's frequency divided by sample size, F over N. Now, the law of large numbers, which this is my little joke for the law of large numbers, the law of large numbers ties these two ideas together. And to introduce the idea, I have a little blurb here from Sherlock Holmes. So I won't read the whole thing, but the individual man is an insoluble puzzle, but in the aggregate, he becomes a mathematical certainty. Individuals vary, but percentages remain constant. So I think I've said that my background was in mathematical finance, particular behavioral finance, trying to kind of decide how people in the market as a whole are going to react to things like stock market bubbles and crashes and things, particularly from the behavioral side of things. How is fear and greed and so on going to play into that? And I was actually discussing with this like day trader guy one time. He was very proud that he was a day trader. Don't become a day trader, you'll lose all your money. Just about everybody who becomes a day trader loses all their money. But he was very proud that he was a day trader, and he was debating me, and he's saying, well, behavioral finance is silly because, like, how can you decide what I'm gonna do? Like, maybe I woke up that day and had coffee, so I'm feeling really optimistic, and if the market goes down a little bit, I won't pull out my money. Or maybe that day I didn't sleep at all the previous night and I'm feeling really down, and maybe if the market slides a little bit, I'm going to pull all my money out. Like, you can never know that. But that's the whole point, is if you said that, the entire stock market, we were going to pick one random person or something, and the entire stock market was going to be dependent on their trading decisions, well, yeah, then we couldn't do any of this. But what we really care about is, what are the 300 million or so, or maybe 150 million or so investors in the US, or even more than that across the globe? What are they doing in the aggregate, kind of on average? Right. So if the one person who had their coffee this morning is probably balanced out by the other person who didn't get a lot of sleep last night. So the law of large numbers, what it says, roughly speaking, is that for a sufficiently large sample size, the frequency distribution that we guess using empirical probability will be close to the actual underlying frequency distribution, kind of from classical probability, or if we were omniscient and we knew the population level parameters. Now, incredibly importantly, there's something called the gambler's fallacy, where people will look at this. Well, let me hide this for a second. Where people will look at this and they'll say, oh, okay, well, what this means is, so maybe I'm in a casino and I see the roulette wheels and I see that it has the last 10 or 15 or 20 numbers that came up, that it lists up there. And I walk by and I say, well, getting 10 reds in a row is very unlikely. Red versus black is, say, roughly 50-50. Getting 10 reds in a row is very unlikely. Well, hey, I look at this particular wheel and I notice that it just got 10 reds in a row. Some people will look at law of large numbers and say, oh, okay, well, that means the next one is more likely to be a black, because getting 11 heads in a row or 11 reds in a row would be even more unlikely, or getting 12 reds in a row would be extremely unlikely. But that's not what we're saying here. What we're saying is something more along the lines of, okay, you watch that roulette wheel and you see 10 reds in a row. But if you watch it for a long time, if you watch it for another, day or two, you're probably going to see 10 blacks in a row as well. So it's not that like there were 10 reds in a row, so black is due, or that like, God is sitting up there and saying, wait, there was 10 reds in a row. If I let 11 reds in a row happen, people are just going to go crazy. I better make the next one a black. No, it's not that the universe somehow corrects probability on an instance by instance basis, but it's that if something strange happens to the left, well, if you watch long enough, a similarly strange thing to the right is probably going to happen as well. That's what the law of large numbers says. So we don't want to make the gambler's fallacy. We don't want to say something like, if we just flip 10 heads in a row, then the chance of getting tails in the next flip is, more than one half, because like, well, we can't get, 11 heads in a row. That would be super rare. That's not what it's saying. In fact, if anything, if I saw somebody flip 10 heads in a row, I would be suspicious that the next head would be more likely to happen, because maybe my probability model that I have, the nice 50-50 heads tails model, maybe it doesn't fit this situation for some reason. Maybe there's something funky with their coin that in the real world makes heads come up much more often. Maybe it's like dented or something a certain way, or off balance, or maybe it's a trick coin. Maybe it's like two heads, on two sides or something. So actually, if I saw 10 heads in a row in real life, I would be more likely to doubt my model and suspect that there's something wonky going on here, and expect that maybe heads are even a little more likely than I originally suspected, than to go the other direction. And so Nassim Taleb, I have a couple of quotes in chapter 4 from him, uh, famous hedge fund manager. And one of his quotes is, the minds of the gods cannot be read just by watching their deeds. So, you know, it is it's a powerful statistical tool to be able to look at an empirical frequency distribution and guess the underlying frequency distribution by that. But we ought not take that too far. We ought not get too confident in ourselves based on just the empirical data. In fact, Nassim Taleb made his money essentially by making bets that were, quote, impossible to come true. So people drastically undervalue them. They're like, it's free money. I don't care if you pay me, $1 or 10 cents. Like, it's free money. I don't really care. It's impossible for that to happen and me to have to pay out. And then when the impossible happened, he would make a lot of money. He'd lose a little bit of money a bunch of times, but when he won, because people were undervaluing those, quote, impossible events, he was able to make money in his hedge fund. And then subjective probability, I think that I'm just going to leave this till later. This is more a discussion for something like Bayesian statistics. But there are a couple of ways to think about subjective probability. One of them is kind of just the way our brains work, right? We go through the world and we do certain things, and sometimes we do something and it turns out good, and sometimes it turns out bad, and we kind of learn from that. So how do we judge, the probability of this thing happening or that thing happening? Well, it's subjective. It's based on our own personal opinions and experiences and so on. Another probably better way to talk about subjective probability is in terms of Bayesian statistics, where we say, when we overlay this mathematical model into the real world and we say, what's the probability of it raining tomorrow? Should I have a picnic or not? And probability maybe represents more like subjective degree of belief in a certain occurrence or whatever it may be than something more objective like frequentist statistics might suggest. But I think we'll leave that until a little bit later. We will take a little aside and discuss some Bayesian statistics later on in the course. Okay, any questions so far? All right, so jumping forward then into section 4.2, the addition rule or the addition property. To build up to the addition rule, we need a little bit of extra background. So we've talked about the existence of an event, like, drawing a jack or better out of a deck of cards or flipping a head then a tail, something like that. So we have an event that typically is some but not all of the outcomes in our sample space, although it could be all of the outcomes or none of the outcomes. But if we have an event, we could also discuss its complement. So the complement is simply the set of all the outcomes in the sample space that are not in the event. So if this was event E, this would be event E complement. Let me write that a little bit better. E complement. Sometimes the complement of an event is denoted E bar or E prime with a little apostrophe to the side. I don't like either of those. E prime kind of has a couple of different connotations, I think. But E bar, I mean, that looks a little bit too much like X bar for me. I know that it's a different context. X is a random variable, so X bar versus E in the event, they're different things, but they kind of look the same. And so I typically would write E superscript C for E complement. I think it's just a little bit better notation, but you might see it any of these different ways. This is like I said, the set of outcomes that are in the sample space, but not included in the event. So if the event E is getting heads on a coin flip, E complement is getting a tails on that coin flip. If event E is the Steelers win the Super Bowl, the complementary event is the Steelers do not win the Super Bowl. So that's the complement of any event. A pictorial tool to help us with some things related to things like complementary events or the addition rule is a Venn diagram. So a very simple Venn diagram like the one we have here. We draw a rectangle, and this rectangle represents the sample space. So we imagine that all of the outcomes in the sample space are in this rectangle. We typically draw circles within the rectangle to represent events. There are going to be some outcomes, maybe like outcome 1, that is in the sample space and also in the event, but typically there will also be some outcomes, maybe outcome 2, outcome 3, that are in the sample space but not in the event. As always, the event could have all of the outcomes in the sample space in it. That's allowable, or the event could have nothing in it, but typically we're going to see some but not all of the outcomes in the event. Now, something very important about this is just a pictorial representation. The size of the circle relative to the size of the rectangle is meaningless. I could have just as well drawn this event, this big or this big. It would be the same Venn diagram. So it's not that like the size of the circle relative to the size of the rectangle is super important. Not at all. We're just cordoning off the idea that there are some event or some outcomes in the event and some others that are not in the event. There are some outcomes within the circle and some outside of the circle. So for example, we can look at the event of rolling an odd number on a standard die. I know that in my sample space in the rectangle are the outcomes 1, 2, 3, 4, 5, 6. I know that my event rolling an odd number contains outcomes 1, 3, 5. So 1, 3, 5 all go inside of the circle representing the event. And that leaves 2, 4, 6 staying outside of that circle, but within the rectangle. So the complement of that event, 1, 3, 5, or rolling an odd number, its complement is 2, 4, 6. Or we could call that rolling an even number. Right? An event is really just a set of outcomes, but quite often we refer to events using words or using a narrative because that's a little easier for us to understand. So I might recognize that the event 2, 4, 6 is it kind of fits with the narrative rolling an even number. And we have a rule for complementary events, the complementary events rule. It says the probability of an event plus the probability of its complement is the probability of the whole sample space. Right? The probability of an event is the number of outcomes in the event over a number in the sample space. And the probability of the complement of the event is the number of outcomes, well, in E complement is the same as saying the number that are not in the event. And if I add up the number of outcomes in the event plus the number of outcomes not in the event, of course, that has to be all of the outcomes. Each outcome either has to be in the event or not in the event. That's all of the outcomes divided by all of the outcomes. That gives me 1 or 100%. So the sum of the probability of an event and the probability of its complement has to be 1. In this setup, it's not super helpful, but where it's quite helpful is if we rearrange it and say that the probability of an event is 1 minus the probability of its complement. This is actually a very helpful tool to use in some situations. In fact, this is kind of like a symmetry, right? I can investigate the event itself, or I can investigate kind of the exterior of the event. I can investigate the interior of the circle directly, or I can investigate the exterior of the circle in some sense, right? So this is kind of like a symmetry that we can exploit in some situations. Sometimes it's not that helpful. Sometimes it's extremely helpful. Let's look at a couple of examples. We'll start out with some simple examples just to kind of get a feel for how this works. So these simple examples, this isn't going to be overly helpful. In fact, it'll take us much longer to solve the problem using the complementary event rule than without it. But we're just trying to get an idea of how this could work. And then we'll see some examples where it actually is quite helpful. So if I'm looking at probability of rolling an odd number, I could rewrite that as 1 minus the probability of the complement of that event. 1 minus probability of rolling an even number. All numbers coming up on a die are either even or odd. So if the number is not odd, it must be even. But I know the probability of rolling an even number, 2, 4, 6, there are 3 outcomes in there divided by 6 total outcomes for rolling a die, or that's 1/2. So probably rolling an odd number should be 1/2, and indeed it is. Again, this didn't save us time. It took us a lot more time, but we're just getting an idea for how the flow of something like this could work in a simpler example before we go to a more complicated example. Or for instance, the probability of rolling a number greater than or equal to 2, 2, 3, 4, 5, 6. Well, that's 1 minus the probability of the complement. Rolling a number that is not greater than or equal to 2 is rolling a number strictly less than 2. But that's just rolling a 1. So what's the probability of rolling a 1? That's 1 out of 6. We want to do 1 minus that. That gives me 5, 6, which is what I expect. Might have been a little bit helpful here because counting 2, 3, 4, 5, 6, I have to count 5 things versus rolling a 1. There's just 1 outcome there. So it makes the counting a little bit easier, although, probably not all that hard to count 5 things. What about something like this, though? So on a roll of 3 dice, compute the probability of rolling a sum that's greater than or equal to 4. This is actually pretty complicated. There are lots of ways to roll 3 dice and get a sum bigger than or equal to 4, like 156 or 355 or 664. We could actually think of rolling 2 dice. So I have a first roll, I have a second roll, and then kind of tacking onto that, like the roll of a third die, I can almost think of a third dimension. Think of going like back into the screen for my third roll. So this would be like 111 in this top little cuboid here, which I'm doing a really poor job of drawing. This would be like 111 that lives in this little tiny cube up here, or like this would be what, like 3 uh 1 1. So I have a cube that has a width of 6, a height of 6, and a depth of 6. So this is going to be all in all 6 cubed, or 216 different little cubes. Right, when we had 2 die rolls, we had 6 squared because we had a square, 6 by 6 square. Now we have this kind of like cube of the 6 by 6 by 6, 6 cubed, or 216. So there are 216 possible die rolls. There's going to be a ton of these that have a sum bigger than or equal to 4. I really don't want to count them all up. But I could look at the complementary event, 1 minus the probability of rolling a sum less than 4. I could ask myself, how can I roll a sum strictly less than 4, rolling 3 dice? Well, I know, for instance, if I roll 3 ones, I get a sum of 3. That's less than 4. That's in the event. And actually, if even one of those rolls goes up to a 2, like a 211 or a 121 or a 112, I'm already at 4. In fact, the only way to roll a sum less than 4 is to roll 3 ones. In other words, the event rolling a sum less than 4 only has one outcome in it. I don't have to count all of the outcomes. There's just one outcome in it. That was an easy event to count. I know that the entire sample space has 216 equally likely outcomes, or 6 cubed equally likely outcomes. So I just do 1 minus 1 over 6 cubed, or about 99.5%. Any questions on this?